Welcome back to a video for Principles of Algorithms. This time we're going to be talking about Gaussian elimination. So we continue our track on linear algebra and systems of equations. Last time we set up this system of equations, we went through solving it, other than we didn't propagate the answers all the way back, and we talked about how we can represent it as matrices. And so now I want to formalize this. I actually want to come up with an algorithm. And the algorithm we're going to do actually is the simplest one that we could do, which also means it's not the best. We're going to talk about Gaussian elimination. And Gaussian elimination pretty much does what we did over here. We're just going to be a little bit more regular with it. We take the value that we want to, so in the row where we want to eliminate a variable, we take a value and we wind up finding the coefficient that will make it so that when we either add or subtract, these things are equal, so they will cancel out. Some things to note about Gaussian elimination, things that we didn't have to deal with in this example, but imagine the simple example of I change the equation to be like that. That's a very real possibility in setting up these equations, but then the process that I went through before doesn't work, mainly because I don't want to divide by 0 here. Multiplying by 0 makes things meaningless, as does the division by 0. So this is not the row that I want to be working with, and what I have to do is I have to swap rows. And actually, in a very general sense, it turns out that you want to swap rows with the largest value. And why is it that you want to do that? Well, remember, we're going to be doing these things with doubles on computers, and doubles are not actually real numbers in the sense of mathematical real numbers. I'm going to do my work here in Scala, while the students in algorithms are going to have to do their stuff in C++. Scala is more pseudocodish, and so that's what I'm going to work in. But you might remember an example of something like this. Now, mathematically, this expression clearly has a value of 0, 1 minus 0.9 minus 0.1, but on the computer it does not. And so what happens there? Well, it turns out that doubles have finite precision, and the fraction 0.1, and hence also the fraction 0.9, when you convert them to binary, they are infinite repeating values. Much like when you convert 1/3 to decimal, it is 3's going infinitely. Well, if you only have finite precision, that gets cut off at some point, and you actually have an error in there, so you're off by a bit. And this happens to be a nice example where we can see that manifesting in binary. Now, things that we don't want to do. Why do I want to find the largest value? And actually notice its largest magnitude. If this had been a -20, I'd actually rather divide by the -20. Even though technically it's a small number with the less than comparison, it has a large magnitude. Turns out really the worst thing that you can do with these numbers as far as accuracy goes is to subtract two numbers that are very similar to each other. And that example that I just did, 1 minus 0.9 minus 0.1, remember that works out to this. And so I get two numbers, the 1 minus 0.9 and the 0.1, that are very similar to one another. And so when I subtract them, it turns out what I am left with is mostly error. To understand this, let's go to a decimal system, and we'll pick a random decimal number. And say I want to subtract these. Now imagine that I'm on a machine that only has 4 digits of accuracy. Okay, well, if I only have 4 digits of accuracy, that means that this longer number wound up being cut off, and this winds up being a 2. Now, of course, that's fairly close, right? I only altered this by half of, or by 5/10,000ths. Okay, so this was tenths, hundredths, thousandths. I altered it by 5/10,000ths to get here. That's not too much. But what happens now when I subtract these two? Okay, the answer should have been, so let's actually 415,927 let's actually copy this, paste it, and go to that 2. So the answer of the problem that I really wanted, if I had an infinite precision machine, would of course been 0.001597. And in the machine, we're going to represent this in kind of a scientific notation. So this is 1.507 times 10 to the minus 3. And let me superscript that. Okay, so that's the answer that we want. But what answer do we get here? Well, we get 0.002, which is 2 times 10 to the minus 3. And as you can see, while originally our error bar was, our errors were fairly small percentage-wise. Okay? The errors that we had in our original formula here were on the order of a few in 10,000. Now our error is on the order of a fourth. Okay, so by subtracting these two values that were very near each other, because of the truncation that happens in here for our finite precision, what had been a small error winds up being a large one. And in general, when you have, so your double precision numbers actually keep about 15 decimal digits of accuracy. But in general, you can't, if you've been doing much math, you can't trust the lower 7 or so digits. You generally only trust about half of your digits, which means that if you're subtracting two values and they are similar, they're basically equal in the first 7 or 8 digits, you've subtracted off the entire real information, and all you're left with is the garbage that was at the bottom. Okay? Now, how does that relate to this? The other bad thing you can do is divide by small numbers. Okay? When you divide by a small number, if that small number had errors in it, the magnitude of those errors get magnified. And you'll note that, so in the first step, the 8 here is a real value, but after we've done one round of elimination, it turns out that all of these values were achieved by doing subtraction, potentially subtraction of two values that were close to one another. If they were two values that were close to one another, we might have magnified or we might have made our errors, our error bars large as a percentage of the number. And then if I divide by one of those numbers, I'm magnifying that error, and basically all I'm doing is calculating an error. And so by sticking with the thing that has the largest magnitude, that means that the numbers that went into it had the largest difference between them, and we feel a little bit better about the math. By the way, this is exactly why the book focuses on LUP decomposition, and why you might find that to be a good idea as well, because while I can swap to get the largest coefficient at the top for Gaussian elimination, and so when I solve this equation, the first step I'm going to do is actually to swap those two rows, and I have to remember to swap the values over in y, my y vector, as well as in the A matrix. And then I would go through and yeah, simplify things out. Even though I do that with the largest coefficient here, it turns out that Gaussian elimination is not as numerically stable as other approaches, and that's why the book focuses on something different. So turns out all I did here was discuss the error bars, but I'm going to cut the video at this point, and we'll come back and we'll write Gaussian elimination in the next